So I can't stress enough that what we started covering really in chapter 4 about identifying and using periodic table, knowing locations of elements, things like that based off of charge and all of that, to now these chapters really build off each other. So if you lose one skill or you miss one skill, you're going to miss something in the future. So right now, for doing these type of balancing equations and stuff that we're doing right now, predicting products and all of that, the skills that you need to be able to have, you need to be able to write both ionic and covalent compounds. Remember, for ionic, you're crisscrossing the charge. So remember, you should be able to recognize, okay, this one has this charge, this one has this charge. For what we're doing with predicting products, if it's a transition metal, remember, we have to reverse and figure out the charge of that transition metal. Chapter 6, we began doing those mole to mass conversions, mass to particles conversions, things like that. That's not going away. That's about to come back in chapter 8. So we're going to combine chemical reactions, balanced chemical equations with the math. So understand that that is not going away. It's not something that you just learn for one test or learn for 1 minute and then forget about it and then it's never happened again. It is coming back. And then ultimately balancing and writing chemical equations is chapter 7, what we're doing right now. I'm trying to wrap it up today. I may not get all the way through everything today. We may have to do a little bit on Monday and then starting with the new material for chapter 8. Kind of key thing is, if you've looked at next week's schedule is messed up. There is going to be some learning that you're going to have to do on your own. I'll prepare a video or whatever for you to review with it, but I do want you to do some of the practice on your own, and I'll explain that more on Monday about how I teach this next unit. All right, so just kind of understand that today we're going to take today's going to seem like I'm kind of backwards doing something or going backwards from what we've been doing with balancing. The skill that we're going to learn today kind of really leads into something that you would do in higher level chems and something that you have to understand conceptually. I do know that they will ask at least one question on the test on this. There's a few, the remaining questions in the remaining questions in active are based off of the skill we're doing today. So our skills that we're doing today. So we've already written molecular equations. All a molecular equation is a balanced, it's a balanced chemical equation. All right, so we've already done that part. The new things that we're going to look at today is a complete ionic and a net ionic. So notice the words ionic. What are the only types of compounds that you think are going to be involved in complete ionic and net ionic? Ionic. So we're going to look at charges again today. So that's going to be kind of where we're heading. All right. So take out that sheet that I passed out to you the other day that I said was for practice that you're never going to turn in and all of that. I want you to look at number 12. The one that looks like this. And I only have one extra copy, so everybody should have gotten one of these. We did a couple of problems on it the other day. We're going to refer to a couple of problems on it today. All right. It's a one pager. It's not hole punched. Let's see if I can find any other extra copies of it. I actually have 2 extra copies of it up front. All right. So, I mean, if you don't have it, you can just write the prompt off the board and just kind of complete it there. but I want you to complete this reaction. I also want you to put phase on there. So yesterday we learned how to identify if it's aqueous or not. So I want you to include that. The reactants should both be aqueous. I'll give you that. It's just the products you're going to have to determine. So I'm not going to give too long. We can kind of go through this one together, but all right. So again, just to kind of guide you, remember you should be able to use the information in the name, knowing both of these are ionic compounds because we have a metal and a non-metal. You need to be able to look up the charge and all of that. So zinc is always a +2, nitrate is a -1, so that means this formula is going to be Zn. That formula is going to be written like that. And then the next formula, Ki, is 1:1. So it's just Ki. From what we learned yesterday, zinc nitrate, it contains a nitrate. What do we know about nitrate as far as its solubility? It's always aqueous. All right. Ki contains potassium, which is a group 1 metal. What do we know about that solubility? Always aqueous. Now, they're going to trade partners. So potassium is going to hook up with one of them, and Zn is going to hook up with the other one. Both potassium and zinc maintain their charge. Potassium's still a +1. It's going to now hook up with nitrate. Nitrate's a -1. All right. Zinc is still a +2. Iodine is a -1. So how will I write this one? I2. All right. Now what we have to look up is see what the remainders are. All right. Potassium is always aqueous. Nitrate is always aqueous. So that one should be easy. Please take earbuds and headphones off your ears too. Just because you have long hair or whatever, I do see them. All right. All right, zinc iodide. So now we need to look. This one doesn't have necessarily clear rules, so we have to check. So we do have a statement about chlorine, bromine, and iodine that it's soluble unless it's with certain things. Is zinc one of those things that makes it insoluble? No, so it's still aqueous. Now, are we finished? Still have to balance. So looking at it, I see that nitrate is out of balance. I have 2 nitrates on my reactant. I need 2 nitrates on my product. How do I get there? All right, so balancing that, and then I come back and balance that. All right, So that's where we're at now. That's really taking all the skills that we've had at this point, putting them together. So there are some yes. That is no reaction. We're going to go further with that today. So I want to show you. I'm going to come back to that particular slide and show you something. All right. So there are some special reactions that I want you to see. And so I talked about predicting synthesis. For the most part, predicting synthesis is fairly easy, but we need to make sure that we're aware of a few things in it. All right. So synthesis combination reactions. If I have a metal plus oxygen, it becomes a metal oxide. So an example of that would be like if I had iron, and we're just going to say that this is, you need to know this because it's a transition metal, but let's just say it's iron 2. All right. That means it's going to be a +2 iron. And I have iron reacting with oxygen gas. That's going to become iron oxide. All right, that's all that one's saying. That one's pretty straightforward. It should be pretty easy. Technically, that is a type of combustion. That's why the little hand warmer things that you put in your pockets when you're camping, that's why those works. That is the reaction that's happening. All right. The next one is a metal plus a non-metal. So whenever we have a metal and a non-metal, we talked about this yesterday with acids and bases reactions, with neutralization reactions. A metal plus a non-metal is going to create a ionic compound that we call a salt. So like potassium and chlorine becomes potassium chloride, magnesium and bromine becomes magnesium bromide, things like that. Those are all just called binary salts. All right. Now, this is where it starts getting a little bit different. So if I take that metal oxide that I created earlier, so if I have iron 2 oxide and I react that with water, it's going to create a metal hydroxide. So over here, and what is the formula for hydroxide? OH. So now we still have to come back and we have to balance it. All right. So I should have 2 oxygens now on that side. And things like that. Actually, if I did it correctly, it would already be there. Because I have 2 hydrogens, 2 oxygens then. Because it's 2 Fe, it's iron 2. So it's iron 2 hydroxide in this case because of the charge. So we just have to make sure that it's balanced and things like that. But it won't become, because water contains the oxygen and the hydrogen, whenever we just add the hydrogen to the other formula, we have to make sure that it balances and maintains charge balance and things like that. All right. The next one becomes when you have a metal chloride. So we have something like KCl. We have a salt. And when that salt reacts with oxygen, it becomes metal chlorate. So this is going to become KClO4, because remember, if we look up chlorates, ion, let me make sure no ClO3 is chlorate. That's what I get from going from memory. ClO3 is chlorate. And chlorate's a -1 charge, so it still reacts 1 to 1. Now we have to figure out some balancing stuff. So here we have 2, here we have 3. So I would have to balance by putting a 2 there, a 3 there, and then I would need a 2 in front of there to get it balanced and all of that. So a metal chloride plus oxygen becomes a chlorate. Let me go back to that and all of that. So those are just some kind of little special things to recognize, because you might not know when looking at that how we would add it together, how we would combine them. So those are ones that you just kind of have to know. I know one comes up in active, but I don't remember them ever testing this specifically. They'll just ask some generic questions about it. Like, they're not going to ask you to write a reaction out with it. Just know that, like, a chloride plus oxygen becomes chlorate, an oxide plus water becomes a hydroxide, and then metal plus an oxygen becomes metal oxide. The metal plus non-metal being a binary salt, that's just general information that I was reminding you for neutralization. All right, so decomposition reactions. Kind of the same thing, just in the reverse. So if I have a metal oxide, it's going to break down into the metal and oxygen. If I have a salt, it's going to break down into a metal and non-metal. If I have a metal hydroxide, it's going to break down into the metal oxide and water. And then if I have a chlorate, it breaks down into chloride and oxygen. And then this one wasn't on our synthesis, but if I have a carbonate, remember that carbonate is CO3. So carbonate is going to break down into the metal. A metal carbonate is going to break down into a metal oxide. So one of the oxygens stays with the metal, and then the other two in the carbon goes to form carbon dioxide gas. No, we can. So if I did magnesium carbonate, it's going to break down into magnesium oxide and CO2. All right. So those are ones that you need to just kind of know. Now, if you're looking at where your solubility rules were from yesterday, if you look on the opposite side at the bottom, it actually tells us some of these. So like sulfides, it talks about an intermediate product. It says it's none. The gas that would evolve is hydrogen sulfide. Carbonates, the intermediate is carbonic acid, and then carbon dioxide gas. Sulfites and bisulfites, sulfurous acid, and then the gas evolved is sulfur dioxide. And then ammonium, when it breaks down, it forms ammonia gas. And then we would have like ammonium hydroxide or something like that. All right, so those kind of relate to this, and I just wanted you to see where that is and know that. All right. Anybody need more time on this one? All right. Go back to that sheet that I had earlier, and let's do some practice with some of these. So the ones that were on there that relate to this, we have number 4, number 7, number 9, and number 10. All of those apply to the ones we were just talking about. Hmm? CO3. Cobalt. Cobalt is CO. All right. And I'm writing the ions down just to have you familiar with what they are. By now, you really should be able to look them up and know and kind of go through. All right, so for number 4, what are our products going to be? So it's going to be cobalt oxide. They're both, that's a positive 2, that's a negative 2, so it works itself out. And then we have CO2. No balance is needed in this one because we didn't add or remove any atoms when we did that. All right. Aluminum's a +3 charge, oxygen's a -2. So what should my formula end up being whenever we get aluminum oxide? Should get Al2O3. Now there we do have to balance. Put a 2 there, 3 there. Ooh. Actually, I'm going to put a 4 in front of aluminum and then a 2 in front of aluminum oxide. All right. KClO3, it becomes the metal chloride, and then it becomes oxygen, right? Is that what they said? All right, and so that one does require some balancing. So if I put a 2 there, 2 there, and a 3 there, it should balance. And then the last one, calcium oxide plus water, becomes calcium hydroxide. Remember that calcium is a +2 charge, hydroxide is a -1. So we end up with that. Now, so going through this and doing these, like I said, those were just kind of reminders of all right, fix that in a minute. All right, so let's look at one of the active questions. So one of the active questions, this kind of relates to yesterday's material as well. It says, which one of the following would form a precipitate when mixed with barium nitrate? So what this is actually asking you to do, you need to do a reaction with barium nitrate for each of these. So we have to figure out what products are going to be formed. So what I can really look at is, so for this one, I'm going to end up with barium sulfate. And I don't really care about my crisscrosses on this because I'm not worried about that. I just need to look at what's in it. And I have sodium nitrate, 3. All right. What do I know about this one as far as solubility? It's aqueous. All right. I need to look up barium with a sulfate. So sulfate, look at the sulfate rules. Tell me if barium is one of the exceptions. All right. So because barium's there, that makes that a solid. Now, that would be our answer. All right. But I want to go through and prove it on the rest of these. So we would have potassium nitrate. That's always aqueous. And then we would have barium chloride, and that should also be aqueous based off of the rule, because barium's not an exception for that. Same thing here. It's going to be lithium nitrate, which lithium's a group 1 metal, so it's always aqueous. And then we'd have barium acetate, which is always aqueous because acetate was one of those that had no exceptions and is always aqueous, just like nitrate. And then the last two, you would end up with cesium, cesium nitrate. Because of the nitrate and because of cesium, it's always aqueous. And then we end up with barium hydroxide. And so that when I look at my rules for hydroxide, hydroxide is soluble except when it combines with barium, calcium, strontium, or a group 1 metal. So insoluble except. So that one ends up being aqueous. So that the last one, D, was the one that was trying to trick you. A was the correct answer on that one for mine. All right. So when it asks you questions about that, I like this, that says which would form a precipitate, which would not, you kind of have to go through those steps of predicting the products for each one to see which products would form a solid, which ones wouldn't. So A is the only one that forms a solid. That is the precipitate. So when you see form a precipitate, it's looking for something that's insoluble. And you have to go through those rules. All right. Getting to today's material. Getting into today's material. So we've already done molecular equations. All a molecular equation is, again, is a balanced chemical reaction. So we know how to balance an equation. We know how to predict products and things like that. So a molecular equation is a balanced equation, or a balanced molecular equation is an equation showing the complete neutral formulas for every compound in reaction. Molecular formula is also going to include the phase of matter, like solid, liquid, gas, aqueous, things like that. All right. The next thing, this is one of the ones that we're adding, is a complete ionic equation. Yes. Yes. A complete ionic equation for every aqueous compound. For every aqueous compound, we will disassociate the ions in solution. So if I had KCl plus silver nitrate. And I react that. That ends up being potassium nitrate and silver chloride. All right. This one is aqueous. This one is aqueous. This one is aqueous. But this one forms a solid. So when I'm going to write this if I'm going from my molecular equation to my complete ionic equation, anything that says aqueous, I'm going to break it up into ions. So I'm going to write it, and it's going to seem like it's long. It is longer, but I would say that's potassium plus 1, and I'm going to write aqueous by it. I have a chlorine in that compound, so I'm going to say chlorine minus 1 aqueous. If there had been a subscript by any of these, like if I had Cl2 there, I would have to put a coefficient of 2 in front of it, and you'll see that as we progress today. All right. Silver nitrate is aqueous, so Ag plus 1 aqueous plus nitrate aqueous, and then coming over here to the product side, only one of them's aqueous, so the only one I'm going to break apart is the aqueous one. So since a solid or an insoluble one is not going to dissolve, it's not going to produce ions. So for this one, I write it exactly as it is. So notice the only thing that I wrote ions for were the things that were not the only thing I wrote ions for were the things that were soluble, the things that were aqueous. All right. So when you're writing complete ionic equations, we only separate the aqueous compounds. Everything else stays exactly as it is. So if it's a solid, liquid, or gas, you leave it alone. But if it's aqueous, we split it into its component ions. Do not separate solids, liquids, or gases. All right. Just make sure everybody has what they need there. All right, so I changed my formula. I changed my reaction up a little bit from the one that I intended to use, but you can use the one that you already have for this next thing. All right, so look at your total ionic equation that you just wrote from that. So we had silver nitrate, potassium chloride. I just replaced potassium with sodium here. All right, so we have silver nitrate. We have a silver ion, a nitrate ion, a sodium ion, a chlorine ion, and then silver chloride is what is the solid, and then we have the sodium ion and the nitrate in our product side. Notice that nitrate and sodium, or in your case potassium, they're the same exact ion on both sides. So if I have something that's exactly the same on both sides of a math problem, what can you usually do to them? Cancel them out. So these are only spectators in the reaction. They're just watching what's happening. They kind of cancel each other out. So when we talk about a net ionic removes the spectators. So anything that's not going to change in the reaction gets pulled out. So the only thing that actually participates in the reaction is silver ion, chlorine ion, and then to make silver chloride. So in the complete ionic equation, some of the ions in the solution are unchanged on both sides of the equation. We call those ions spectators because they're just watching the reaction happen. So regardless of what TV announcers and all of that say about fan influence on the game, the fans don't really influence the outcome of the game. The players influence the outcome of the game. Coaches influence it to some degree. It was mostly the players. All right. The spectators are there. If they're there, they're there. If they're not, they're not. The game will still go on. All right. Well, not for professional because they need the money. But if you're just going to go play a pickup game of basketball, you don't care if anybody's watching you. All right. All right. So now I'm looking at my complete ionic equation. So again, this is what would be my complete sometimes you'll hear it referred to as total ionic equation. So complete ionic equation, total ionic equation is the same thing. And now we need to get to what we want to call our net ionic equation. So to get from the complete ionic to the net, I'm just going to get rid of anything that repeats itself. So my net ionic equation, I just removed the spectators. So when we're looking at this one, we're only looking for the species that participate, and that's the net ionic. So my net ionic, what do you predict the net ionic will be? So what are the things that are participating? So I should have an Ag plus 1 aqueous plus a chlorine minus 1 aqueous reacting to form, right? So I should get that. And then that's my net ionic. So that's what it is. All right. So the big thing is going from complete ionic to net ionic. You just remove the spectators. Now, in active, if you're ever asked a question and you have your balanced molecular equation and it's just asking for the net ionic, we can skip complete ionic. I only do complete ionics if I'm asked to do them. For the net ionic, I'm going to look for the product that is the solid, liquid, or gas, and then my reactants are whatever ions make it up. So if I knew that AgCl was my solid, I can just reverse that and know what ions make it up. So you don't feel like you always have to do the complete. Only do the complete ionic when it asks for it. All right. Does anybody need more time on this one? All right. So let's go back to our one that we did earlier on the page. We did zinc nitrate. You should already have it written down on your sheet. And that formed zinc iodide and potassium nitrate. All right. And so yesterday we learned if everything was aqueous, it's no reaction. So let's just proof of concept why. So this is my balanced molecular equation. My complete ionic, L-E-T-E. All right, my complete ionic is going to look like this. Let me erase that and write it correctly so that we can see it. -1. All right, so that one took up a lot of space. That's why I don't like writing complete ionics. Now, if I wanted to go from here, which one of these would be spectators? All of them. So if I asked you to write a net ionic, everything's a spectator, it's just watching the reaction happen. So that's why we say no reaction, because there's nothing that we can prove happened here. Everything's an ion because it's in solution. The only way we can witness something happen would be to remove all the water, to evaporate it out. All right. So again, this one was just proof of concept. The things that I want you to notice that I did. So like notice there was a subscript of 2 on nitrate. So notice I wrote 2 nitrates there. Notice that I had 2 Ki, so I had to have 2 potassiums, 2 iodines. Over here, notice that I had a subscript of 2 on iodine, so I wrote a 2. I had 2, so I have to show those as coefficients. So when you go from molecular to complete ionic, anything that's written as a subscript comes up as a coefficient in front of it. All right. Because ions won't have a subscript unless it's a polyatomic ion and it's for specifically one thing. All right. So I would like for you to try this one on your own. So I have chromium 3 nitrate reacting with iron 2 sulfate. So I want the balanced molecular equation, the complete ionic equation, and the net ionic equation for this. All right. So for the balanced molecular, you should have ended up with this. So balanced molecular, we should have ended up with two chromium 3 nitrates. That's aqueous plus 3 moles of iron sulfate. That's aqueous would react to form chromium 3 sulfate, and it ends up being aqueous because chromium doesn't meet any of the requirements for sulfate to be insoluble. And then iron 3, so it'd be 3 iron 2 nitrates. And again, nitrate is always soluble, so we get all aqueous. So because I see all aqueous, I already know my net ionic, right? I know it's no reaction, but complete ionic we can still do because I want you to be in the practice of that. So for chromium, I'm going to have to show that as 2 ions of chromium 3. For nitrate, I'm going to have to show that as 3 ions of nitrate. For iron, I have 2 ions of iron 2, and 3 irons of iron 2, and 3 ions of sulfate, 2 ions of chromium, 3 ions of sulfate, 3 ions of iron, 2 ions of sulfate. So you should have gotten 6 ions of nitrate, because 2 times 3 is 6. All right, so again, notice the 2 here comes from there. The 6 of nitrate comes from the 2 times the 3. The 3, the 3, the 2, the 3, the 3. 3 times 2 is 6, and that's the 6. All right, one more practice and we'll be done. All right. Now, so I'm gonna kind of not make a disclaimer here. This is these particular questions students find frustrating I don't think it's frustrating because you can't understand it. I think it's frustrating because inherently most people are kind of will choose the lazier path that they can. Let's say it like that. And the complete ionic ends up being a lot of stuff. When you're typing these into active, all right, this is where I'm going to be specific. If it's asking for a complete ionic and active, when you have to type it in cold, you have to do each thing: the coefficient 2, the element, the ion, the charge, aqueous, active. All right. So you have to do each one of those parts in order to get it right. If you forget aqueous on one of them, it's going to mark the whole question wrong. So just recognize that that's going to happen. Yes. Let me answer one question at a time. So I'm trying to remember where the blank was. I think we went from yesterday. I assigned like 1 through 10. It's the 11 through 17, I think. Yeah, some of them are net. Not all of them are complete ionic. So some of them are net ionic. You still have to write the charge and the phase. All right. So let's look at one more and kind of look at this one together. All right. So on the test, On the test, the way that they're going to ask it, they're going to ask on the test the question that I remember seeing. If they ask anything about ionic, they'll ask what the net ionic reaction of a acid-base reaction is. So I'm going to get to that one, and I'm going to do that down in the bottom white space in just a minute. The net ionic equation for every acid-base interaction or neutralization reaction is always the same. So I'll show you that in just a minute. All right, so it says complete and balance the following reactions, determining in each case if a precipitate is formed. Write the molecular equation and the molecular equation, the complete ionic, and the net ionic. All right, so I have ammonium sulfate and barium nitrate. All right, things we need to know. Ammonium, that's NH4 with a +1, right? Sulfate, SO4 -2. Barium, Ba +2. Nitrate, NO3 -1. So when I write my formulas for this, so when I write my first part for this, I get, it's going to take 2 ammoniums to react with 1 sulfate. So I get NH4 with parentheses 2 SO4. And that's aqueous because ammonium's always aqueous. All right. I get barium nitrate with nitrate surrounded by parentheses and a subscript 2 because it takes 2 nitrates to react with 1 barium because barium has a +2 charge. That's always aqueous because nitrate is always aqueous. Now, rearranging it, we're going to end up with ammonium's going to find a new partner, and barium's going to find a new partner. So what's ammonium's new partner going to be? Nitrate. Because it's always got to be the one that's the negative charge, right? And then barium's new partner is going to be sulfate. All right. So since this is 1-to-1, what do you predict the formula will be? NH4NO3. Looking at these two, what do you think the phase is going to be? Or aqueous. This is always aqueous. This is always aqueous. So this is like a super soluble compound. All right. Barium and sulfate. Sulfate has some rules, so we need to see, is barium one of those triggers? So this one is going to be our solid. So when we go through this one, we get NH4NO3, BaSO4, and then coming through to balance it, I put a 2 in front of NH4NO3, and then barium sulfate is our solid. Now, I'm going to skip a step because I want y'all to see this. I already know my net ionic equation here. What's going to be my product of the net ionic? All right, because the product of the net ionic is always whatever the solid, liquid, or gas is. What are the reactants going to be? The ions that make it up. So I would say so like I said, if you know the balanced molecular equation and it doesn't ask you for a complete ionic, you don't have to do it. You can skip that step and go straight to there. If it's asking you for complete ionic, which this is the part that students don't like to do because it's tedious, All right. You would have to go in there. Anything that's an ion, you split up. So I split up my ammonium. I split up my sulfate. I split up my barium. I split up my nitrate. I split up my ammonium. I split up my nitrate. And then I leave barium sulfate together. And then ending it up, I have my sulfate and my barium. I just reversed them. And then I have my solid. All right. So all right. So think back to yesterday's notes. Think back to yesterday's notes. What is involved in a neutralization reaction? What are the reactants always going to be for neutralization? Mixing an acid and a base. All right. Acid plus base makes water. And what's the other product called? All right. Yeah. All right. So if I'm ever asked for a net ionic of a neutralization reaction, what is the only thing in that reaction that's not aqueous? What's the only thing that can't dissolve in water? Water. All right. So, water is a liquid. Now, the reason why water is actually a covalent compound. But the reason why we're doing this. All right. So, the reason why I write water as HOH a lot of times is so that you can recognize ions involved. There are two ions in water. What are the two ions that make up the net ionic for water? What ion are you getting from the acid? What ion are you getting from the base? So again, the reason why I write it is HOH, so you recognize you get a hydrogen from the acid, you get a hydroxide from the base. All right, so the net ionic of a acid-base reaction is always hydrogen ion plus a hydroxide ion reacting to form water, H2O. Water is a liquid, so therefore it cannot technically it's not aqueous, so you have to have that. It is aqueous on this side because it's ions on this side. All right. So at this point, you should be able to answer all questions in active for Chapter 7. If you cannot, you need to seek help either through watching supplemental videos from like Melissa Barabel or Tyler DeWitt, or going back and reviewing the notes for this week through the videos, things like that. We have covered all of Chapter 7's topics. Yes. I personally do not because I coach. If you go to TLC, the best person to get with is if you can find Mr. Mitchell, if he's doing math. He is very good at chemistry.
Is that the dude that does the check?
Yes, he is. Miss Dunn can probably help you with this, but she might not with net ionics. All right, she can do balancing equations and all of that, but they don't do this in regular chem.
Shoot, maybe I should do that.